Yes, first, sorry if there's background noise. I am traveling today, so I promise only 3 minutes of background noise if there is any. First, I want to talk a little bit about Armstrong International and who we are, in case you aren't quite sure. We are a global company. We've been around since 1900. We are a fifth generation family-owned company. Right now, the fifth generation is CEO, sixth generation kids, so not really working in the company yet, but I'm sure within the next few years they will be. We invented the inverted bucket steam trap in 1911, so that was our first foray into steam, and we've been advancing through steam, air, and hot water ever since. Um, I don't want to go through too many technical parts here, but I want to focus today on what's happening with the presentation we're having. So Armstrong believes in optimize, minimize, and decarbonize. And what we're going to talk today is about the optimize phase. And the reason we do that is because we know that there's 70% of rejected energy in a system. And so we can use that waste heat, which Austin will be talking about, and we can recover that and put that back into the system. And this is what will give any of the customers that you're looking at an opportunity to actually save in OpEx, save energy, and save their CO2 emissions as they choose to electrify or make a path towards electrification. And then lastly, our journey as a company started with steam traps, but we did move into the service industry and doing audits since the 1980s. And we've been moving closer and closer to helping the circular thermal initiative go forward since that time. And so now we're right in the throes of it. For the last 4 or 5 years, we've been doing pinch studies and very in-depth thermal mapping of systems. And so some of the solutions that we get from that, as you can see here on the screen, and these are the average paybacks. Please don't, take these as they're coming from the Bible or anything, but this is the normal paybacks that we see if you want to fully decarbonize your system as you move forward. So with that, I want to send it over to Austin.
Thank you. A quick introduction about myself. I'm Austin Schirk, and I'm a thermal engineer at Armstrong. My team specializes in doing full audits on factories mostly. We go into a full thermal mapping, then we'll do a pinch analysis on every waste heat source and heat sink in the facility. And then we come up with projects out of that we do a full presentation on to the customers. This process usually takes a couple months for each site. And what you're about to see are a few of the end projects that we came up with at a couple different sites that we've done this year. So let's get into it. Just a brief overview on the first process. We're going to talk about regenerative thermal oxidizers, or RTOs. You'll see them in a number of different industries to treat emissions that those send to atmosphere. We'll go through that process after this, but just some of the major users of RTOs, the automotive industry, anything with painting, printing, paper making, electronics manufacturing, pharmaceuticals. You'll find them in any industry that has any sort of pollution. A brief overview on how the regenerative thermal oxidizer works. Your exhaust stream comes into the RTO. Depending on what's present in that, you have a condenser first to condense out any solids that you can. Then it goes into the burn chamber where it's held at a high enough temperature to promote oxidization. So any pollution that's in that exhaust stream gets burned away. And then coming out, you either have heat recovery on that or you go straight to the atmosphere. It all depends on what kind of RTO the customer has, what their initial investment was, if they have somewhere they can use that heat. And feel free to stop me at any time if there's questions. I know we've got time for discussion at the end, but we can also do it while we're going through. So a brief overview on the specific RTO process we're going to go through. This process is a steam oven, so they use steam to cure a specific monomer. And then that steam comes to the RTO mixed with fresh air. So they take that through a chilled water condenser. You can either use chilled water or cooling tower water, depending on your process. This specific process, the monitor they have will congeal if it's above a certain temperature when they condense it. So they have to, that's why they need to mix it with fresh air and use chilled water to cool it. Once they condense out everything that they can in the condenser, that airstream continues to the RTO, gets burned away, and it goes out of the stack. In the process we're going to look at, they didn't have any heat recovery on the stack or on the condenser. So they've got two options for heat recovery. On the RTO condenser, they've got about an 80 degrees Celsius, 175 degrees Fahrenheit temperature that's going into that condenser. That's because that steam is mixed with enough fresh air to bring it down below that 85-degree congealing point. So you've got just over 10,000 pounds per hour of, we're only looking at the water flow in that condenser because that's what's going to be condensed out. And that's currently cooled chilled water. And then the exhaust is just over 300 degrees Fahrenheit, 13,000 pounds per hour of airflow, and it goes straight to atmosphere. So should we recover heat from one or both of these streams, and which one can we get more energy from? So we'll look at the RTO exhaust first. So that 320 degree Fahrenheit exhaust, let me start back with, this site has an existing hot water loop for all of their air handling units and a number of their processes. This is a relatively new site, so they've already de-steamed a lot of their AHUs, which is one of the first things we look at when we're going to sites. Can you de-steam any process that doesn't need steam? So the site has an existing hot water loop. So because this is a very high temperature exhaust stream, 320 degrees Fahrenheit, we can recover that into a rather high temperature hot water loop. But as you can see from the diagram here, we can only get about 500,000 BTUs per hour out of that exhaust stream. So you can save just over 200 metric tons of carbon per year on heating that hot water loop with natural gas, or $15,000 a year in cost savings. So relatively small savings on recovering the heat from the RTO exhaust. Now, if we go to the condenser side, so we've got all the steam leaving this oven mixed with air, and then we have to condense all of that steam to get it out of the airstream. Currently, they use chilled water for this. They're going straight back to the chiller. So that's an additional expense to get rid of that steam and that energy. They're wasting the energy from the steam, and they're paying to get rid of it. So if we switch that heat exchanger, they have incoming city water all the time to this facility. They consume that city water in the process, and they need to heat that water up to, I think it's 80 degrees Celsius the entire time. So they have just over 200 gallons a minute of city water coming in all the time to this facility. If we switch the heat exchanger from chilled water to city water, we can condense that entire stream down to 23 degrees Celsius. They may need to finish cooling with chilled water, but all the savings that they can get from using that heated up city water and not using the chiller to cool that condensate are shown here on the right. So just in recovered heat to that water that they're going to use in their process, they can save $180,000 a year in natural gas costs. And similarly on the chiller savings, because electricity is so much more expensive than natural gas, chillers generally have we're going to talk about COP, coefficient of performance, later, but chillers generally have a COP of around 4.5, or they takes 0.8 kilowatts per ton of cooling. That's a rule of thumb that we use in most cases when we're talking about chillers. So because the electricity in this case was 4 or 5 times more expensive than the natural gas, your savings from the chiller are roughly the same as your savings from natural gas, with a much higher carbon reduction than on the RTO exhaust. So 200 metric tons to 2,600 metric tons a year. So these are both heat recovery options off of the RTO, but it's all, do we want to do one or both of these? It's all dependent on what the customer needs, what the customer wants, what's their end goals. Are they looking to decarbonize as much as possible, or are they looking for projects that only have under a 7-year payback? We're going to spend most of this time on heat pumps and that project that comes next and optimization on those, but we just wanted to cover a quick direct heat recovery project before that. And stop me if there's any questions on these before we get into heat pumps, or we can talk about it at the end as well. We're going to start with a generic optimization, a couple slides on heat pumps before we get into the specific example that we want to go through. Heat pumps are a little more challenging to size, install, and to just in general go through than a direct heat recovery process. So here we have we're heating water in this process from 80 degrees to 200 degrees. There's a total natural gas cost to do that, whether you're using steam to heat that water or whether you're using direct natural gas fired boilers. Or you can completely decarbonize and use an electric water heater or electric boiler. But as you can see, the cost in this particular instance is over almost 4 times what it would be to use natural gas. And as we keep going, you'll see that's a common theme. The electricity to gas price ratio is a huge determining factor in what projects we can install. So once we get to the point where we start to consider a heat pump, we have to figure out how we want to size that heat pump, what outlet temperature we want, what's the MMBTU or kilowatt output that we're going to have. You can, on one end, size the largest heat pump possible with the highest outlet temperature and the most amount of decarbonization. If that's your customer's end goal is decarbonization, then maybe that's the heat pump you go with. You can see here, in this specific scenario, it would save about $141,000 a year, and the heat pump has an outlet of 175 degrees Fahrenheit. As you decrease the size of your heat pump, you decrease the percentage of the total heat you need that comes from electricity in that heat pump. But you also increase the coefficient of performance of that heat pump, the amount of energy you can get out versus the amount of energy you put in. So you're creating a smaller piece of that total energy, but you're creating it more efficiently. So somewhere along the line of making the heat pump smaller, there's an optimization point, economically speaking. And a lot of times, not a lot of times, sometimes that's what the customer is looking for. They can't put in a heat pump that loses money. They want to have the lowest operational cost possible. So if that's the customer's end goal, we go through and size the heat pump at every outlet temperature. We've got a program that'll do it. And we'll find their optimum outlet temperature for the heat pump. And then they continue to heat the rest of that process with steam or hot water. On the other hand, we can do the same thing and compare it with just carbon emissions. Obviously, if you do the entire thing with electricity, you have no carbon emissions from your facility. You can do that with just a heat pump as well instead of an electric boiler. So if you have the option to fully decarbonize with an electric boiler or with a heat pump, ideally would go with the heat pump because of that coefficient of performance that it has. For the same amount of output, you can use 3.5 times less electricity than using an electric boiler in this scenario. But as you can see here, if we go to the economically optimized heat pump, the carbon emissions go up. So with each different With each size your heat pump gets smaller, you have more carbon emissions because you're still using natural gas to finish heating your water stream. And the third optimization point for the heat pump is return on investment. The smaller you make your heat pump, the less costly that heat pump is. Generally, your piping smaller, so you have less associated cost with the equipment installation. And you usually have a greater utility savings to a certain degree. So we can calculate the return on investment for that entire heat pump installation. And if that's the criteria that the customer is using to pick their projects, then they would use the 145-degree outlet heat pump. So those are generally the criteria we're using when we're sizing a heat pump based on what the customer needs.
I just want to jump in here real quick and mention that on the previous chart that Austin was showing, there are customers that'll say, hey, I want to fully decarbonize. Well, okay, when the cost comes around, they're singing a very different tune. So the message that you would need to go in as you're working with these projects is, okay, is it better to save nothing because you're not going to spend the money, or is it better to save 3,000 metric tons at this time and top up, and then later you can fully decarbonize the process through a larger heat pump or whatever it is. So that's the thing to keep in mind when you're talking to whoever you're doing these studies for.
And that all of these numbers that you're showing are based on your natural gas and electricity prices for now, or for a last 5-year average, depending on what your customer wants you to use. And not ideally, but most likely natural gas costs will continue to rise, and that gap between the electricity and natural gas will get smaller. So all the calculations you did to optimize that size of your heat pump will change as those costs change. So we'll get into the heat pump example. This one specifically is for a paper machine. So we take the exhaust from the paper machine and bring it back to, there's multiple air inlets on every paper machine, but this is to one specific air inlet. So if we just follow this diagram through really quick, the paper comes in and gets pressed to squeeze out as much water as you can before it comes through and gets dried by Yankee drum is the term, but that's heated with steam and comes out the other side as a sheet of paper. So there's exhaust from the Yankee and from the pre-dryer, but they get mixed together and they come out as a single exhaust stream. So we'll compare direct heat recovery on this exhaust stream to direct heat recovery with a heat pump on that exhaust stream. So using just direct heat recovery, we'll get into the diagrams after these numbers. I know it's usually easier to see that way. You can recover almost 7 million BTUs directly into the exhaust stream, heating your incoming air to, on average, about 140 degrees Fahrenheit. Now, most sites, we break it up into winter and summer cases when we're sizing anything with outside air, and we'll do an average that way. This one, we did that as well, but these numbers just show the average for the full year. So your heat recovery is going to be less in the summer and more in the winter as your delta T grows and shrinks. Here's a better look at it. When you're doing direct heat recovery, if it's an option, it's usually your simplest option and it provides your best payback. There's not as much machinery to install. It's just usually a couple heat exchangers, some piping and pumps, and you get what you can get out of that exhaust stream. So in this case, you can recover just over 6 million BTUs of energy, which correlates to, in this case, almost 7 million BTUs of natural gas because of that direct burner efficiency that they're using in this air intake. So right now they draw in outside air and they have direct burners to heat that outside air to 500 degrees Fahrenheit or something like that. We're not going to be able to reach anywhere near those temperatures with the direct heat recovery or the heat pump, but anything we save on heating that with natural gas can be seen in their operational savings and natural gas emissions. So if we just use direct heat recovery, we can save just over $400,000 a year in this scenario, with just over 3,000 metric tons of carbon emissions saved, and a project payback of just under 7 years, which can be important for some customers, if not most customers, when they're looking at installing a new project. So from that exhaust, instead of doing direct heat recovery, we can do direct heat recovery and have a heat pump. If you can do direct heat recovery, we always recommend it. We don't recommend installing a heat pump without, looking into direct heat recovery first, because like we always say, direct heat recovery has an infinite COP. It doesn't cost you anything besides a couple pumps, usually, and electricity, just the installation of the equipment. So we'll do the same exact direct heat recovery as in the first example, but on top of that, we'll add a heat pump. This heat pump came out with a COP of 5. We'll look into the heat pump on the next slide more, but the cost savings on the heat pump are just over $100,000. So it saves you $350,000 in natural gas, but it costs you $240,000 in electricity to run. And all these numbers are very specific to the site with their electricity and natural gas prices. You can install the same heat pump in Europe and the savings will be much higher because their gas and electricity prices are a lot closer. Or if you go, we were just in Pennsylvania, and they had natural gas straight from a well that was very cheap. So this heat pump would have a negative payback because they're getting natural gas almost for free. So it all just depends on where you're at and what those prices are. So we'll dig into the heat pump more directly. Up here, it's just a 1,550 kilowatt heat pump, so 1.5 megawatts, a rather large heat pump. For the source, we've got exhaust of 197 degrees coming out of this paper machine, and we're going to cool that all the way down to 155 degrees. We want to stay above the dew point just because there's a lot more energy if you can condense the water in the exhaust stream, but it comes with a lot more headaches as well. You need to install piping to take that water and either recycle it in your system if you want. You need different materials to build the stack, stainless instead of carbon steel. So in a lot of cases, we try to stay above the dew point if there's enough energy there to recover. So this heat pump would take the energy from the stack, so 1.2 kilowatts or 1.2 megawatts in energy, and upgrade that heat from 180 to 239 degrees Fahrenheit. So we're taking that same heat from the stack at a lower temperature and injecting it back into the inlet at a much higher temperature. And we can get the airstream that we're heating up to 224 degrees Fahrenheit instead of the 143 with direct heat recovery. And just a note on the coefficient of performance, the COP of the heat pump, if you subtract the direct heat recovery from your heat output, you'll get the compressor power that you have to input to the heat pump to get that. And then if you divide your total output by that compressor power, it gives you the COP, the amount of energy you need to put into the heat pump to get a certain outlet. So now if we get into putting all this together in a project, obviously this project is a lot more complex and costly than just doing direct heat recovery. You've got to add an extra coil in the intake air. You have to add the heat pump, all the piping that goes with that, the supports that the heat pump needs to go on. So it's a lot more complicated and costly, but you save almost twice as much carbon installing that heat pump on top of your direct heat recovery. So if your customer wants to decarbonize more of their emissions, instead of just looking to decrease their operational costs, they would want to look in this heat pump. And that's in this scenario, the heat pump also provides an additional operational cost savings. But the project payback is longer due to the increased costs and complexity. So we will just a quick comparison on those two options now. Like I just said, the heat pump adds a lot more cost and complexity system, but it does increase your operational and carbon savings. And I have a little note in there that those operational savings aren't always there depending on where these heat pumps are installed. So a big part of the studies we do is identifying the costs of the facilities, what their electricity and natural gas costs are for the last couple of years, and what they project them to be moving forward. Because we can install this same exact project somewhere and all these numbers will be negative. And the customer's goals determine how we size these projects. What do they want out of this? Do they want maximum decarbonization? Do they only want projects that have a 3-year payback? Do they want to decrease all their operational expenses? That's usually the main driving factor in how we end up sizing these projects. We'll give them the maximum decarbonization options, but we'll also have to give them the best option for what they want. A few of the key takeaways from this is there's always multiple ways to recover heat from a source. I mean, you can do direct air to air, air to water. You can recover partial, you can recover all of it. You can condense the airstream or just recover the sensible heat. But it all just depends on what the customer's needs are in the end. The electricity and gas pricing is huge for any heat recovery project, but especially for heat pump projects. And then condensing water out of an airstream is where you can see a lot larger heat recovery numbers, but you also have to take into account what you're doing with all that water, how acidic it is, and what materials you would have to use to install this that'll affect your costs. And finally, on heat pumps, they're a great tool to help decarbonize, but we don't go into a site pushing a heat pump. We go in, we need to optimize your system, we need to recover heat where we can, and then if you still want more out of it, we can put in the heat pump. It's not the first choice, but it's better than putting in an electric boiler or anything along those lines. That is it on that presentation. Any questions on heat pumps or direct heat recovery or anything with Armstrong?
Thank you, Austin. This is really helpful. I may ask, I had missed earlier just the electricity and gas prices kind of used as a baseline, realizing we're in an area that, relatively speaking, electricity is a little cheaper. And so I'm just trying to kind of get a sense with your baselines here, if these numbers are similar or maybe a little higher, the ratio of electricity to natural gas.
So I don't have specific prices in this presentation, but if your electric to gas ratio is around 4, usually we can install a heat pump that has a positive payback. Coefficient of performance of around 5 is our general target for these heat pumps. We can go, much higher or much lower depending on the size of it. If we look at this, the biggest size heat pump here at a 3.5 COP, and they go all the way down to over 7 if you want to have a really small heat pump. So it can't do much work for you, but it will have a positive payback.
Sure. No, that helps to at least kind of get a rule of thumb.
You can get a rough idea from the natural gas only versus electric only there of what the spark spread is.
Mm-hmm. Yeah, or here it's about 4 times, give or take.
Well, thank you. Yeah.
So that rule of thumb of the electric gas ratio of 4, that is units converted already, right? So that
Correct. Yes, kilowatts to kilowatts usually will convert natural gas to kilowatt hours, and then
right. Okay. Yeah, because it's always complicated when you're comparing therms and kilowatt hours, right? And
yes, it is.
I was hoping you were going to throw those numbers out for the students and for me to sort of develop our intuition when we just start looking at something. Should we even analyze it, right? And
I'll add a little slide before I send the presentation over today. So it can be in your notes for later.
that's awesome. You don't happen to remember offhand what your dollars per kilowatt hour rate? No? Sorry to put you on the spot. Oh,
I think this is
we've got an engineer in our midst. Good job.
Yeah, this one we're looking at. I don't know if this is your exact, but these are pretty
12
standard.
cents. Yeah. Okay.
Both
Awesome.
$5 are pretty.
12 cents and $5. Thank you.
Austin, I'm curious if you guys do much heat exchanging between not just water to water or water to air, but like flowable solids or like slurry type materials.
Slurries, yes, on occasion. Most of the time, if they're cooling that product, they're already using water to cool it. So we'll just take the water side so we don't have to interact directly with their process. And that's how we like to do a lot of the heat recovery projects, if we have that option, is not interact directly with the process, but either an exhaust stream that they're not touching already or on the water side of their cooling.
So you guys have done projects for that, and you guys have I guess the hardware or like the equipment that does that well.
Yes, and we have done projects on like sewage wastewater that recover heat out of that. So there's specific heat exchangers you have to use if you've got solids in the recovery, in the waste heat that you're trying to recover.
Okay. Yeah, thank you.
I may mention what Caleb's talking about is something in the Nebraska, Iowa area that's common. Many facilities have very warm, I'll call it wet distiller's grain. Think of this as, like coming out of a beer distillation, and it's fairly warm. It's right now, typically they just let the heat dissipate. And a good question is, given that that's an industry that's has strong financial incentives to decarbonize, trying to think of, would you put a heat exchanger right above them? What would be maybe the way you would think about the engineering? Because many of them say preheating water to the boiler would be a real obvious alternative.
Yeah, we've usually got two options. The first one would be to use one of those special heat exchangers that can accommodate the flow of something with solids, or some sort of immersion coil into the tank that you're trying to cool. And
Okay.
you would pipe your water or whatever you're trying to heat through that, your boiler feed water for the process. And that's usually the more common way, is some sort of immersion coil.
Okay. That's helpful to kind of learn from your experience what might be a better option.
So in one of these examples, I think you had a heat pump lift of 20 degrees or something like that. It was 140 to 160 maybe, or 160 to 180.
So we've got 180 to 230.
Yeah, well, right. And so this gets at my question, which is, what's our high temperature limit? So if we're working with some strange process that has really high temperatures and we're still trying to lift those temperatures up, we start running into problems with the critical point of the refrigerants, right?
Yes. So Armstrong's high temperature heat pumps, the limit is 248 degrees Fahrenheit, 120 degrees Celsius, with about a 90 degrees Celsius inlet is the highest source temperature we can take.
Excellent. Thank you.
And we can have a theoretical debate if you want, but what we found, and it's not just us, independent researchers have found, once you start going over that 120C, you don't get a lot of benefit from the heat pump side with the current refrigerants that we have today anyway, for sure. What you should be doing at that point is flashing to steam and then using MVRs if you want to go to a higher temperature. And the last thing I would say is when customers are asking for 248 or 240, whatever the number is, they don't always actually need that. They're just replicating what's coming out of their PRV or something like that. So if you can get down to what does the process actually need, you might be able to lower that temperature and bring it down into the heat pump range. So if someone's asking for 300 degrees, do they really need that? Or is that the steam temperature that they're using to then heat water? You know, that's now it's a water process, a hydronic process. So I just wanted to bring that up mainly from a technical perspective, that once you start getting above 120C, it is much better to start using MBRs at that point if they really need it, which are
Yes.
very expensive, by the way.
Okay, yeah, those are great points. Thank you, Peter.